Hello everyone. Today I'm going to talk about streaming submodular maximization under a case-set system constraint. I am Ehsan Kazemi and this is a joint work with Haba, Moran Feldman and Amin Karbasi. In many fields of science, we are often encountered by a variant of a subset selection problem where we have a collection of choices among which we would like to pick a set that maximizes the utility. For instance, in product recommendations, we have a set of items and the goal is to find a subset that satisfies the user the most. In experimental design, the goal is to run the most informative subset of experiments to reach conclusion. In data summarization, the aim is to select the most representative subset of data points from a massive dataset. In all these examples, we have a ground set of items, tests, and data points, and a utility function that specifies how satisfied the users are, how informative the tests are, or how representative the data points are. In all of these problems, the goal is to maximize the utility while satisfying some natural constraints. For instance, in product recommendation, we might have constraint on how many items at most we may propose to a user. In the experimental design, we might have a cost constraint. Or in data summarization problem, we might have a categorical constraint that states how many data points from a category of data can be included in a summary. Of course, without any structures, solving this optimization problem is computationally infeasible as we have to enumerate all possible choices that is usually exponential in the size of the data. But what is a good structure? In this paper, we consider submodularity as a non-trivial property that encapsulates many applications. Submodularity is preserved under many operations and it is amenable to optimization techniques either exactly or approximately. Submodularity captures the intuitive diminishing returns property, where the added value of including an element, for example a sensor, to a context, for example a group of sensors, decreases as the context in which it is considered gets larger and larger. More formally, for a submodular function f and to sets A and B, where A is a subset of B, the marginal gain of adding a new element S to set A is always larger or equal to the marginal gain of adding that element to set B. A submodular function is said to be monotone if we're to sets A and B, where A is a subset of B, the utility of set B is always larger or equal to the utility of set A. Submodularity has application in every field of science. It has applications in machine learning, in neuroscience, in economics, in operations research, and many other fields. In many applications of submodularity, the data arrives at a very fast pace. There is only time to read the data once, and random access to the entire data is not possible, and only a small fraction of the data can be loaded to the main memory. As a practical example, consider the case we want to find the most representative frames from a video stream without storing the whole video. So here's a very fundamental question. Is it possible to summarize a massive dataset on the fly when at any point of time we have access only to a small fraction of data? More concretely, in this paper, we consider a very general form of constraint submodular maximization where the goal is to maximize a submodular function f over a set of feasible solutions I in the streaming setting. Generally, f could be non-monotone and constraints are imposed by the application. While in the offline setting, the problem of maximizing a non-monotone submodular function subject to general types of constraints is fairly well understood. In the streaming setting, when the elements arrive one at a time and the memory footprint is not allowed to grow significantly with the size of the data, the landscape of constraints submodular maximization is much less understood. In this paper, we propose the first streaming algorithm for submodular maximization subject to a general case-set system constraint. Next, I will first define constraints we consider in this paper and then explain our proposed algorithms. The hierarchy of independent systems is quite rich and expressive, containing many classic examples which are useful for modeling real-world applications. The simplest example is the k-cardinality constraint when you have a limit of k on the size of feasible sets. K-metroid, as a generalization of many constraints from metroids to matchings, is a set system over M metroids where each element appears in ground sets of no more than k metroids. In k-extendable systems, as a generalization of k-metroid, adding an element to a feasible set requires the removal of at most k elements in order to keep the resulting set feasible. For a k-set system, a natural generalization of k-extendable systems, the ratio between the size of two bases is upper bounded by k. The problem of submodular maximization in the streaming setting first was initiated by the work of Badanijwa et al. They studied the monotone submodular maximization under a cardinality constraint. A 2015 paper studied this problem for monotone submodular functions subject to intersection of k-metroids. Buchbinder et al., Chekuri et al., and Feldman et al. Considered non-monotone submodular maximization subject to more general constraints such as metroids and k-metroids. Given all these recent works, there still remains two open questions. We know that submodular maximization for non-monotone functions is more challenging, and usually it's easier to first tackle the problem for monotone functions. So the first question is this. Given an algorithm for monotone functions, can we convert it to an algorithm for non-monotone functions? And as a second question, is there any streaming algorithm that works under more general settings such as k-extendable system or even k-set system? In this paper, we propose a novel framework that converts streaming algorithms for monotone submodular maximization into streaming algorithms for non-monotone submodular maximization. We use this framework to design the currently tightest deterministic approximation ratio for submodular maximization subject to a k-metroid constraint. We also propose the first streaming algorithm for monotone submodular maximization subject to k-extendable and k-set system constraints. Moreover, for general submodular maximization in the streaming setting, by using our proposed framework, we obtain O of k log k approximation ratio for k-extendable constraints and O of k squared log k approximation ratio for a k-set system constraint. Now we are ready to explain our framework for converting streaming algorithms for monotone submodular maximization into streaming algorithms for non-monotone submodular maximization. Our framework assumes access to two procedures. Access to R instances of a data stream algorithm for maximizing the submodular function under the given constraint by the problem, and the constraint offline algorithm for the same problem. Assume S is the feasible solution provided by the streaming algorithm, and A is the set of elements that the algorithm keeps in its internal memory. Every time an element arrives, the first instance of a streaming algorithm is called and updates its internal data structure and returns the set that it decided to remove. The removed element is passed to the next instance of a streaming algorithm, and this process is repeated for all the other instances. Once the stream ends, we run the offline constraint algorithm over the internal memory of each instance. The final solution is the set with the maximum value from the outputs of all instances of the streaming and the offline constraint algorithms. There is a desired set of properties for an algorithm to be applicable by our framework to provide a solution with a guaranteed utility. Note that set A can be quite large and therefore cannot be stored by the algorithm if we want it to remain a streaming algorithm. To bypass this issue, the streaming algorithm should accept only elements whose marginal gain is larger than a threshold. In this sense, it provides a trade-off between the memory complexity and threshold. Also, the algorithm should bound the utility of the final solution in a tractable way. Based on these properties, we say that an algorithm is an alpha-gamma approximation algorithm for non-negative values of alpha and gamma if it returns two possibly random sets S and A, where S is an independent set. And for every independent set T, the expected utility of set T union A is smaller than alpha times the expected utility of set S plus gamma. Finally, we should point out that these are common properties among almost all the streaming algorithms we are aware of. Now we are ready to present the first theoretical result of this paper. Assume the streaming algorithm is an alpha-gamma approximation algorithm and the constraint algorithm is an offline beta approximation algorithm. Then our framework returns a solution S such that the expected value of this set is larger than the value you observe here, where this bound is a function of R, alpha, beta, and gamma. Note that gamma controls the trade-off between the memory complexity and the approximation factor. We can also find the best approximation ratio with optimizing over the value of R. So far, by designing a framework to convert monotone streaming algorithms to algorithms for non-monotone functions, we have answered the first open question affirmatively. Next, we explain our streaming algorithm for k-extendable and k-set system constraints, and then we show why our framework is applicable to this algorithm. The technique at the heart of our algorithm is based on growing a set to which elements can only be added. For a stream of data, by using some standard techniques, the value of optimal value is guessed. Then, by using a threshold defined as a function of the optimal value and the marginal gains, elements are placed in different buckets. The number of buckets is a function of the size of the largest feasible set, and elements with smaller marginal gains are placed in buckets with larger indexes. Once the entire input has been processed, the algorithm combines buckets AI into each possible output sets S. Each set Sj is constructed by greedily taking elements from all buckets AI where I module H is J. H, which is the number of sets S, is proportional to log of k, where k is the parameter of the k-extendable system. The internal memory of the algorithm, A, is the union of all buckets AI, and the final solution provided by the algorithm is the set with the maximum value among sets S. Now we present the second theoretical result. In the paper, we prove that under k-extendable system constraint, our streaming algorithm returns a set S such that for any independent set T, f of S is larger than f of T union A minus tau 4 divided by 4h times 2k plus 1. First, note that this guarantees the performance of algorithm for monotone submodular functions, and second, we observe that our streaming algorithm is a 4h2k plus 1 tau 4 approximation algorithm, and hence we can apply our framework. By combining these two, we are able to prove that our streaming algorithm is O of k log k approximation algorithm for the problem of maximizing a non-negative submodular function subject to a k-extendable system constraint. We could also extend these results to the k-set system constraint. In this paper, we extensively compare our proposed algorithms with other streaming algorithms and state-of-the-art offline algorithms over several randomly generated graphs, social networks, and many real-world applications, including movie recommendation, Yelp location summarization, and Twitter data summarization. In one of our experiments, we consider a non-monotone submodular graph cut function over Eredor-Shreni random graphs under an independent set constraint. It is straightforward to show that this is a Dmax extendable system where Dmax is the maximum degree in the graph. We observe that our streaming algorithms outperforms the other streaming algorithms, and also we could see that the non-monotone version of our algorithm is the better one. At the end, I would like to warmly thank you all for your time and your attention.